Hello? 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 Can you hear me? Titli? Hello? 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 Hello. Can you hear my voice? Hello. Is it clear? Hello. 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 Good afternoon to everybody. Hello.
Hello?
Hello. Can you hear me?
Yes, sir.
Okay. It's all right. Now let us start on behalf of before 15 minutes because this is the maybe last class. Okay. I told one of the important questions in the final examination. Okay, madam.
Okay, sir.
Now let us see. Just in the black one, first unit is there. So that is the real number system and completeness. Now, in this unit, especially already I told what is the concept of real analysis. Now, some of the real numbers must be analyzed in the systematical order. Hence, the following axioms are satisfied. Now, one is the field axiom, and the second one is the order axiom, and the third is the completeness axiom. Okay. Now, these three axioms are very important concept, especially in a real number system. Now, this is the meaning of RNS means that is the real number system. Now, real number system means that is the complete ordered field. That is the simple definition now in the concept of real analysis. Now, it is the commencing from real number system is that is the meaning of completeness ordered field. Now, some of the real numbers must be analyzed in the systematical order, and hence the following axioms are satisfied. Students, listen carefully. Axioms in the similar name is properties, postulates, and conditions, and the laws. Okay. Now, these are all similar names. Now, already we have learned in previous class, previous concepts in the algebraic structure. Now, in the algebraic structure, that is the commences from group theory. Now, in the group theory, what are the main concept of algebraic properties? Closure law, associative law, and existence of identity, existence of inverse, and commutative. Now, last but not least, that is the distributive property. Now, here the closure and associative, when those axioms are satisfied, that is called a semi group. A semi group having with monoid, having with identity, that is called a monoid. A monoid having with inverse. Inverse is the G4 axiom. Now that is called a group or groupoid. Now, when the group must be satisfied, when the commutative property is satisfied, that is called commutative group or an abelian group. Now that is the structure of a group. Okay. Now in the same manner, we must define the ring definition is also there. A circle from R cross R to R be any non-empty set of a mapping is said to be a ring if the is said to be a ring. Now, what is the difference between the group and ring? Group, it satisfies only one axiom are satisfied. Only one binary operation must be satisfied, not only one axiom. Okay. Group, it satisfies only one binary operation. Binary operation means a binary sign or binary composition. Now, these are all similar names. What are the binary operations? That is the usual operations or ordinary operations are addition, subtraction, multiplication, division. These are all binary operations. When we must know the addition, then automatically we will define the subtraction is there because additive inverse is subtraction. And the multiplication is also defined when we must know the multiplication concept. And according to the multiplication, we will define the division of this part because that is in the same manner a cross b or a into b. Some a into b equals to x, that is the b equals to x by a. So that is the multiplicative inverse is division. That is the concept of multiplicative inverse is division is there. When we must know the any two algebraic compositions, when we must know the any two binary operations, then automatically we will define the another two binary operations are also well defined. In the same manner, what is the ring? A circle be any one of the binary operation or binary. Now that is the when the proper part we must read as binary operation or binary composition or binary sign. Okay, binary symbols. Now those are all equal. But here especially What is the addition? Where here the concept is where through the binary operations and using with the binary elements, we must define the group and ring. Ring it satisfies at the same time both operations are satisfied. Now with respect to the addition and multiplication. Now that is the structure of a group is G under addition or G under multiplication, whatever it is. Okay, there are so many examples. In the same manner, real numbers and natural numbers. All the natural numbers are positive integers. Especially now, this is the introduction of real number system. And before the real number system, we must know the algebraic concept. Without algebraic concept, we can't define, we can't learn the real number system part. Because now that is the formation of analyzation. Analyzation is also analyzation means through the algebraic concepts, that is the preliminary part. Now that is the primary part is complete ordered field. What is the field? Before that, before we will learn the field definition, and first of all we must know the ring, and before that we must learn the group definition. Okay, already that is the difference between the group and ring. Group, it satisfies only one binary operation, or next binary operation is also there, either with respect to addition or multiplication is there. Okay, but the ring at the same time, both operations must be satisfied. What are the both binary operations? Okay, Ponam and Titli, both are follow is there. Now, this is one of the important concept, and before the concept is, okay, ring. Now, ring at the same time, both binary operations are satisfied. Students, listen carefully. This is one of the most important concept in a real analysis. And analysis means that is the analyzation. What is the analyzation? Already we have finished the third block is there. That is the Riemann integrals concept. And before that, first block concept is that is the real number system and completeness. And what is the real number system? Now that system of the formation through the real numbers, now that must be satisfied. That must be satisfying field exam, order exam, and completeness exam. And before that field, we must learn the ring definition. Ring at the same time, both operations with respect to the addition and multiplication through the binary operations with respect to the binary elements. Now then we must define the ring definition. Students, listen here. Circle from R cross R2 be any non-empty set of a mapping is said to be a ring. If it satisfies first one, R under addition must be an abelian group, is an abelian group. Okay, abelian group means R1, R2, R3, R4, R5. R1 is the closure exam, R2 is the associativity, third one existence of identity R3, R4 is the existence of inverse, and R5 is the commutative property. Okay, when these R1 to R5 must be satisfied, that is called R and addition is an abelian group or commutative group is there. Second one, with respect to the multiplication and a non-empty setting, non-empty set of a mapping, with respect to non-empty set, with respect to the binary elements through the binary elements. Now, with respect to the multiplication composition, that must be a semi-group. Now, in the using multiplication composition, R1, when R1, R2 must be satisfied, and with respect to the multiplication of non-empty set, formed a semi-group is there. And the third one is the semi-group distributivity property. Multiplication distributes with respect to the addition. Suppose here A, B, C or any three elements given in the non-empty set. Now here A of B plus C equal to multiplication, left side multiplication distributes with respect to the addition AB plus AC. And in the same manner, B plus C of A. Now A must be distributes, multiplication distributes at right side. Now that is B plus C of A. Now that is the BA plus CA. Especially in the distributive property must be involves the commutative part is there. Now when the left distributive and right distributive both are must be equal. When we are both distributive properties are must be equal. When the commutative property must be satisfied is there. Okay. Now here when the left distributive law, right distributive law must be equal. Now then automatically multiplication distributes with respect to the addition and a distributive law holds good. That is called a ring. Now last but not least here. Now that is the 3 minutes more to 1:30. Now and before that we must introduce the concept of analyzation. So that's why I told repeated as an rapid part. What is the concept of what is the basement of analysis? Now that is the algebra. Without algebraic properties, we can't form a formation of a analyzation. Now that is the field exam. Okay, what is the field? Now here be any one of the important operation. Dot be any one of the important operation. F cross F be any non-empty set of a mapping is said to be a field. Before that, first of all, we must define the non-empty set of a mapping. Means F cross F2. That is the Cartesian mapping. F be any non-empty set. Mapping is said to be a field. First one, it has a unity. What is the unity part? A into 1 equal to 1 into A equal to A. That is the multiplicative identity or unity element is there. Okay. Now that it has a unity, that is the simple 5 fingers of the part. Middle finger must be defined the unity part, and middle finger of left side and right side. Now it denotes the concept of commutative, and little bit finger is the no zero divisors, and right thumb is also that it has multiplicative inverse. So already already have that is the ring of the part. With respect to the definition of a ring, now we have learned what is the every field is an integral domain. Now that is the group introduction to groups and rings is there. So that is the main theorems of algebra. Every field is an integral domain, and but integral domain is not a field. That is the converse of the theorem need not be true. Okay. Now in the same manner, we must define the field definition. Yeah, now that is the first one. It has a unity, it is commutative, and the third one, any non-zero element must possess with the multiplicative inverse. That is called a field. Okay, that is the field exam. Now, second one is the order exam. Order exam means to express the in between the real numbers, to denote to express the relation, order relation in between the any two real numbers, either less than or greater than or less than or equal to or greater than or equal to, whatever it is, according to the trichotomy conditions. So now that is the simple order relations, less than, greater than, less than or equal to, greater than or equal to. Okay. Now when this to express the relation in between the two real numbers, that is called the order exam. Either A less than B or B greater than A. Either A less than or equal to B or B greater than or equal to A. So in between the relation is called order of this part. And third one is the field exam. Field, first one is the field, second one is the order exam, third is the completeness exam. What is the completeness exam? Any non-zero element must possess with the multiplicative inverse. That is called completeness exam. Any non-zero, okay, just listen carefully. Okay, completeness exam means any non-empty set of real numbers which is bounded above, it has supremum. That is the completeness exam. Okay, student, listen carefully. Now, any non-empty set of real numbers which is bounded above means that is the upper bound of this part. It has a supremum. Supremum means that is the least upper bound. That is the LUB part. Okay, now that is the completeness exam. Okay, this is the complete ordered field. That is the simple concept of real number system. Listen, students, see this one. Now all the just see and observe, enter these are all logarithms 1.2. So that is the real numbers as an ordered field. All the properties involved in 1.2, that is the additive property. A1 is the commutative and A2 is the, this is the blender of this part. A1 is the closure and A2 is the associative. A3 is the existence of identity and A4 is the commutative. A4 is the inverse. Okay. In the same manner, multiplicative is also there. M1 is the closure with respect to the multiplication. M2, M means that is the multiplication of the second law, associative. And M3 is the existence of identity. A dot 1 equal to 1 dot A equal to A. And M4 is the multiplicative inverse. And M5 is the commutative. And D1, that is the distributive of the left distributive means D1, right distributive is D2 is there. Now, already I told here, enter all the properties, that is the algebraic properties must be based upon the algebraic concept. Okay. So students, listen, see and observe here. What is the, okay, this is the definition of, hello? Okay, very nice. Very nice joining all the students. Now, this is the one of the important session. See this one of the important theorems in the first unit. Please note down. Please note down. Now, this is the 1.2.11. This is the triangle inequality. Now, in the examination, this question is one of the short answer. Triangle inequality 1.2.11. If A comma B be any two real numbers, absolute of absolute A. Absolute means that is the modulus. Here A and B be any two real numbers, then absolute of mod A minus mod B is less than or equal to absolute of A plus or minus B. And again it is less than or equal to mod A plus mod B. Okay. Now this concept must be based upon the what is the meaning of absoluteness. And before we are taking here A, B, any non-zero element, that non-zero element must express one of the real number. A and B is there. There are two real numbers here. So before that, A lies between and minus absolute means now it is the lies between negative and positive of the part. So A lies between minus of mod A and plus of mod A. Okay. And again, plus or minus B is also lies between minus of mod B and plus of mod B. So, according to the definition of absoluteness, minus of mod A plus mod B. Again, that can also be written as minus of mod A and minus of plus is minus, that is mod B is there. So, enter my negation is common. Now, common of the negation, according to that value is less than or equal to, okay, minus of mod A plus or minus B. So again, minus of mod is we are taking the positive, that value is an equivalent to A plus or minus B. So again, that value is less than or equal to mod A plus mod B is there. That is the natural of this part. Okay, again, absolute of A plus or minus B less than or equal to, absolute means that is the modulus. It read as absolute or modulus. Mod of A plus or minus B less than or equal to mod A plus mod B is there. Okay. Now, according to this one, now mod A means the mod A means absolute of A equal to absolute of A minus B of plus B. Less than or equal to absolute of A minus B plus absolute B. Because A minus B, that is the notion of X is there. Mod X plus B less than or equal to mod X plus mod B. Now replacing of X by A minus B. So in the same manner, we are at right side of the absolute of B value converting into at left side. At left side, mod A minus mod B less than or equal to mod A minus B. Say that is the first equation is there. And in the same manner, mod B minus mod A. And according to mod B can also be written as mod B minus A plus A. And applying the above inequality, mod B minus A less than or equal to mod B minus A plus mod A is there. And again, mod B minus mod A less than or equal to mod of B minus A. So we are applying here, mod of B minus A can also be written as mod A minus B is there. Thus, mod of mod A minus mod B less than or equal to mod of A minus B. because now there is the triangle inequality is there. Now this is also one of the important short answer. Now we are getting the easily to get the 5 marks is there, because short answer, that is the simple that is the matter of every block we are consisting. There are 2 short answer questions. Now 2 into 4, 8 marks is there. Okay. Now second one, what is the principle of mathematical induction? And already we have learned in the previous section up to from lower classes, we are learning more times, many more times. That is the induction principle. Okay. Now that is the plus one, simple concept, plus 1 times. That is the induction principle. Okay. What is the inductive set? Here A and B are any two. Okay, any 2 sets are there. Okay. Now A contained are equal to B, B contained are equal to A, or A subset are equal to B, B subset are equal to A, then that implies A equals to B. That is the simple induction principle. And according to this one, now plus 1 times means that is what is the principle? When let n be the set of natural numbers, write the principle of mathematical induction. And that is the simple 1 mark question is there in the fill in the blanks. Okay. That is the suitable answer. Okay. Either objective type or fill in the blanks. No, this is the write the principle of mathematical induction. Here let n be the set of all natural numbers. Here n being a natural number and P of n be a statement about the natural number. Put n equal to 1, P of 1 is true. And second one, P of n is true and implies P of n plus 1 is true. Then P of n is the, here n being a natural number, P of n is always true for every n being a natural number. That is the simple concept of principle of mathematical induction. Students, this is the one of the important, and in the same manner, state and prove well ordering principle. Okay. Now this is 1.3.3. Now this is one of the important theorem in the first unit. Okay. So we are just, you have to marking here 1.3.3. Now we have to through entire the analysis concept must be based upon the principle of mathematical induction and well ordering principle. Okay, what is the well ordering principle? Here the order condition must be applied through that is the concept of WOP. Now that is the short form. WOP means that is the complete of the abbreviation is well ordering principle. Okay, PMI means principle of mathematical induction. Now what is the statement of well ordering principle? Suppose every non-empty subset of n means the set of all natural numbers. Every set must contains one of the subset is there. Okay. Now every non-empty set of natural numbers, it has a least element. That is the simple statement. Okay. Least element means that is the one is the least natural number. 1 belongs to n. Okay. Every non-empty subset of natural numbers. Suppose before we are taking given the set of elements are natural numbers, and then their subset must be, it has a least element is there. Now that is a simple proof. Here A, B, any one of the subset is there. That subset must consisting some of the natural numbers. So here n be the given the set. That set is the set of natural numbers. We are taking some natural numbers, write the one of the subset is denoted by capital A. A contains capital N. Now it read as A contains N or A is a subset of N. Because before that subset is also non-empty, means it is consisting some of the elements. Suppose before that, without there is no elements, we are nothing to prove. In the same manner, let us suppose that given the non-empty subset, it has no least element. No least element means define a set, capital B, right? The capital B is by B, any one of the set. Here set of, given the set is natural number, set is denoted by capital B. Set of n being a natural number and such that m being a natural number. In between the relation is m is less than or equal to n is there. Okay, implies m is does not consisting of capital A. Now we are taking 1 be the least element is there, 1 belongs to B. And for if 1 does not belongs to B, then 1 belongs to A. now 1 would be least element of given the subset. Now that is the contradiction of this part. Our supposition given the subset, it has no least element is there. In the principle of mathematical induction, here n being any one of the element given in the set, then m is less than or equal to n, and implies m does not here the in the same manner. Okay, m belongs to m being a natural number, but in between the relation m and n, m less than or equal to n. So then automatically m is less than or m does not consisting, or m is does not belongs to a. We claim that in the mathematical induction n plus 1 is also consisting b, but in the same manner, for if n plus 1 is does not consisting b, there exists a number m such that m being a natural number, but m less than or equal to n plus 1. Here m belongs to a is there. Now replacing of n plus 1 by m is there. Here n plus 1 is also belongs to a. Okay, now here if m less than n plus 1, then m less than or equal to n, and m does not consisting of the given the subset. Now that is the contradiction of this part. Since by our supposition that a has no least element. Suppose a has no least element means here p being any one of the existing of the element belongs to a, p less than n plus 1 means n less than p lies between n and any real number lies between two consecutive integers. Okay, and in the same manner p lies between n and n plus 1. Okay, now here p does not consider, p is also belongs to a. Here n belongs to b and n plus 1 belongs to b. Suppose given the set of all the set of elements are natural numbers. So here m does not, by definition of define the set capital B, m does not consisting a, given the subset is empty. Empty means because there is no elements. Now our supposition is wrong. So given the subset it has no least element is wrong. Okay, because it is given the subset is at least some of the elements. Those elements it is consisting one of the at least one least element is there. So given the subset it has a least element. So the students listen carefully. This is the well ordering principle. Okay, so 1.3.3, this is also one of the important in the final examination, and how to write the rational number set. Okay, now entire all those concepts before especially in the first unit, what is the analyzation concept, what is the RNS. Okay, now what is the rational number? Rational number is denoted by capital Q. Now it has the Cartesian form, m by n is there. In the numerator, m being an integer, in the denominator of small n represents being a natural number. So rational number is denoted by p by n or p by q, whatever it is. And every in the that is then the formation of rational part, fraction part, and in the numerator of the element must be an integer, and in the denominator of the element or natural number. Now that is called the rational number of the form. That is the okay. Now roster form is capital Q equal to set of x such that x being a real number and there exists n being a natural number. What about the relation? Here n into x is also being a integer. Okay, now a real number which is not a rational number, without rational number, that is called an irrational number. Okay, if it is not a rational number, that is called an irrational number of this part. Now that is the expression is denoted by capital Q. That is the return of the set is Cartesian set is nx is also being a integer. Student, listen carefully under 1.3.6. That is also one of the important theorem. That theorem is Archimedean property. Okay, Archimedean property. This is also well-ordering principle and Archimedean property. These two theorems are very important in the first unit. Now, what is Archimedean property? If it is x comma y being both are any two rational numbers, and x be any element that must be greater than 0, there exists n being a natural number. What about the relation? Nx. And in between the n and x relation is n into x, that must be greater than y. Okay, here x and y be rational numbers and x is greater than 0 and n being a natural number such that nx is greater than y. Now what is the proof of this theorem? If x is greater than y, then n equal to 1. If x equal to y, then n equal to 2. So x lies between let 0 less than x less than y. We are taking one of the rational number, put x equal to p by q formation, and y be the one of the element. So that is also rational number. Then the form is r by s. What about the relation p comma q comma r comma s? Now enter all the small letters are being in natural numbers. Now in the relation between n equal to rq plus 1, that is the by the division algorithm concept, nps. Now multiplying n lies between nps and rq. So nps by rq, nps by qs is greater than rq by qs, because QS is also applying enter the part over R, NP by Q, and S is also cancelled here. It is greater than R by S is there. By taking here, NX is greater than, so P by Q formation is P by Q is X, NX is greater than, R by S is the Y. So we are getting the value is simple concept, NX is greater than pi. That is the Archimedean property. Students, please note there is no time. Now some important questions must be denoted here. That is the definition of 1.4.2. Simple. What is the countable definition? This is the countable and uncountable sets. Okay, countable and uncountable sets. Now this is the one of the concept. Listen carefully. What is the definition of defined countable set and uncountable set? First of all, we must learn the countable set and uncountable set. So a set is not countable, no, that is called the uncountable part. Now what is the countable? That is the de-enumerable. There are so a number of similar names. Okay, enumerable, de-enumerable, and countable. Okay, now here A and B be any two non-empty sets. If there exists a connecting in between the sets, then the relation is bisective relation. Now, what is the bisective? A relation which is bisective when the surjective and injective, there is the one and on two. Then those conditions are satisfied. That is called a bijection of this part. In between the sets, that is A and B is there. Okay, that is the similar sets. Now here A is similar to B. Now similarly of sets is an equivalence relation on the sets. Here is a set capital A is said to be a finite, because there is some fixed elements. That set is called finite, and so the number of elements which is not finite, that is called infinite set. Now finite element set is denoted by, that is the fixed elements, set of 1, 2 and so on, n values. For some fixed here n being a natural number. Now that a set before that, countable set before that must be a finite is there. Students strongly believed here every what is the countable set, and before the countable set defined the part must be based upon that set must be a finite is there. So yes, capital A B, any one of the set is said to be countable. First one, A is empty. Empty means that set is empty, means there is no calculation because there is no elements. Then automatically it is countable. Second one, a capital A is a finite set. Then now it prescribes the some elements are, there are fixed elements given in the set. So before that capital A is finite. And third one, A is similar to natural numbers of this part, because given the set and the entire the set of the elements are natural numbers. So natural number sets, the set of natural numbers equivalently, natural numbers must be an infinite set of this part. So according to these three conditions, then automatically we must define the given the set is countable of this part. If there is a countable set defined the part of, then the relation is bisective relation. Okay, because capital A is the set n is a set onto capital N. Countable set, and sometimes that is called de-enumerable set or enumerable set. That is the simple similar names, because some others may be referred de-enumerable and enumerable in the place of countable of this part. Now, one of the example countable definition, capital N is set natural number set countable set, because then the function of this part defined the mapping is f maps n to n, and capital N is the domain of this part, and remain capital N is the codomain of this part. Simply now that is the defined of the mapping, then the relation is f of small n equal to n is. Now that defined the relation in between the mapping relation is bisective is there. that bisective f of x equal to x. That is the identity mapping. Okay. Now here the countable set of the define the mapping of the relation is identity mapping is there. So then automatically the set of natural numbers is a countable set. And in the same manner, f maps here capital N to 2n. 2n denote the because natural n be the natural numbers and the 2n is denoted is the set of positive even integers. Now f maps capital N to 2n. Capital N means here that is the domain and the 2n even integer set is denoted by range of this part. Now here n be small n being a natural number, then the relation is f of small n equal to 2 small n. Okay. Now when the what is the bisective of this part? Now given the set of the relation is defined, it is 1 1 and on 2. So set of even integers is also one of the finest example of countable set. The set of integers is also countable. Okay. Okay, this is also one of the important relation. Okay. Now, see this one in the countable and uncountable sets. There are some of the important theorems, students. 1.4.6, that is the simple relation because any subset capital N is countable because the natural numbers of the subset is countable of this part. 1.4.6, that is the simple part, and because some theorems statements must be asked into the fill in the blanks or objective type, whatever it is, match the following. Okay. 1 point countable. So remark is also one of the important here.
Excuse me,
Now
sir.
there is a hello.
Sir,
Hello. Tell me.
ఆబ్జెక్టివ్స్ ఉండవు కదండి సార్ ఇప్పుడు
మీ దానికమ్మా ఎస్పెషల్ ఎస్ ఆబ్జెక్టివ్ వితౌట్ ఆబ్జెక్టివ్ మీన్స్ ఈ సిస్టమ్ నుంచి తీసేశారని చెప్పారు. ఒకవేళ ఉన్నా దానికి కూడా మనం రెడీ అవ్వాలి కదమ్మా.
ఓకే
Okay. If it is possible, if it is in the old version, there is no problem. Without this one, directly questions to given short answers and SICs, there is no problem. Directly, we must save. Okay.
ఓకే సార్ థ్యాంక్ యూ సార్
Okay. Okay. All right. Now 1.4.8. This is also simple statement. A countable union of countable sets is countable. The union of countable sets is countable. This is also simple statement. And rational numbers of the set is also countable. This is also one of the finite important theorem in the essay question. 1.4.9, please note down and in the final examination. 1.4.9, please note down. Rational numbers of the form p by q or m by n, whatever it is. And according to this one, we must construct the rational numbers of the table. And according to the rational numbers, set of rational numbers of the set, it must be a countable of this part. 1.4.9, this is also one of the important theorem, especially. Okay. And again, see the page number 12. Page number 12, 1.4.13. Okay, so page number 11 is there. Okay. Students, just please stay on the line. Please stay on the line. 1.4.11. Page number 11. The set of real numbers is not countable. Countable definition, countable theorem is the set of rational numbers. Second one, the natural numbers. Second one, the set of real numbers is not countable. These two theorems are very important in the final examination. Don't mislead here. The set of real numbers is not countable. 1.4.11 is there. Okay. And again, 1.4.13, root 2 is dash. Rational number, not rational number, whatever it is. Root 2 is not a rational number. Because this is also one of the short answer, SEQ 1.4.13. Now, how to get the solution? This is one of the problem. Root 2 is not a rational number, means that is an irrational numbers of the part. Now, that is the formation nx equal to, okay. nx. That is the formation is irrational form is nx. Now, before that, root 2 equals to x and x square equal to 2 is there. Suppose root 2 equal to x is there. Here x being any one of the rational number. Now rational number form is p by q. Suppose root 2 equal to p by q, that is the possible version. And in the p by q, denominator of this part, q will be any non-zero element. Okay. Now that non-zero element means here p and q both are integers, prime integers are there to each other. That is one is the greatest common divisor of the part. Here the greatest common divisor of the element is denoted by the replacing of p and q. So root 2 equal to p by q, and square root can be converting into that side. Here 2 equal to p by q whole square. So that is p square by q square. Here p square equal to 2q square. Here q is an integer. Hence, q square is an integer and 2q square is also even integer is there. Now, when it is that 2q square is an even integer implies here p square is also even integer, because 2q square is an equivalent to p square is there. Then automatically p square is also even integer. And before that, when we are taking at least one of the even integer is there, suppose p be any one of the even integer, then the square of the element is also even integer. Okay, because 2, we are taking the 2p is there. Then it is a square of the part is 2p whole square means 4p square. So that is p square equal to 4m square. That is also one of the element. And again, p square equal to 2q square is also, and one of the, we are taking the another element is there. And replacing of the value, p square is 4m square. Okay, 4m square equal to 2q square. And after the simplification, here 2m square, 2 is also cancelled on both sides. Now 2m square equal to q square. Here q square is an even integer, and before that q is also an even integer. Here p and q both are even integers. Now that is the contradiction of the part. Here that is automatically, that is the relatively prime. What is the relatively prime? In the same manner, relatively prime is also called mutually prime or co-prime. Okay. Now, when m and n, greatest common divisor of the p and q, or greatest common divisor of m and n equal to 1, that is called relatively prime or mutually prime or co-prime. Now, our assumption here, root 2 equal to p by q, and when it is with respect with p and q of the greatest common divisor 1, that is also wrong of the part, because the given part 2 root 2 is not a rational number. Now, this is also one of the important problem in the final examination 1.4.13. Okay, students, listen carefully. Okay, what is the definition of a bound, a lower bound and upper bound? Already we have told in the previous classes in the lens of Riemann integration concept. Lower bound, upper bound, greatest lower bound means infimum, least upper bound is supremum. Okay. Now, listen, just see and observe here. What is the completeness axiom? Already, and from the beginning of this class, already I told here, what is the completeness axiom? Any non-empty set of real numbers which is bounded above, it has a supremum is there. And state and prove Archimedean property, nx is greater than y. Okay, that is also repeated here. And 1.5.18, just we have to write, we must write in this version also there. Okay, what is the Dedekind's property? Okay, Dedekind's property, Dedekind's completeness property. Okay, here a and b be any two non-empty aggregates of the real number set. Then the ordered pair a and b, a comma b is then the small bracket. It has ordered pair of a and b means, and before that, if the intersection of any two sets must be empty is there. The union of any two sets must be a real number. That then, and a less than b, for all small a belongs to capital A and small b belongs to capital B. When these three conditions, the intersection of any two sets must be empty. The union of any two subsets must be a real number. Okay. Now the Dedekind property states that either A capital has the maximum and maximum number, and capital B has the minimum number. Okay. Now, in the final examination, this is also one of the important completeness exam, if and only if dedicants property. This is also one of the important. What is express the equivalence of completeness exam and dedicants property? This theorem is also one of the important 1.5.21. Please note down. This is one of the finest theorem, especially in the real number system. Okay, don't miss it. Now, this is also one of the important in the final examination. Okay. Now it is completely based upon the definition of dedicants and completeness property. Student, listen carefully. This theorem is also very important. 1.5.21 is there. Now that is the completeness axiom if and only if the dedicants property. Okay. Don't miss it one. Don't miss it. Especially you must thoroughly practice in this theorem. 1.5.11 is there. Okay. Now here, this is the main concept in the first unit, and next one, that is the second unit, is the open sets and closed sets. Now directly only important concept, please note down. According to this one, in the open sets and closed set. Okay, what is the open interval? Now it is completely first of all, so we must define the what is the interval. Okay. Now a subset capital A, B, any, R, B, any one of the set of real numbers set is there. And according to the real number set, the set of real numbers, we must express the one of the subset is denoted by capital A. Now here A, B, any subset, that subset must be contains capital R. It is called an interval. We are taking any two elements given in the subset. Here X, Y belongs to capital A and Z being any one of the real number. So any real number lies between two consecutive integers. Those consecutive integers elements must be involved in the subsets of the elements. So here ZB, any real number lies between remaining two elements or subsets of the elements. So now Z is also consisting of the belongs to capital A, consisting or capital A. Okay. Now here intervals, especially what is the open interval? Students, listen to this one. Without open interval, we can't define the open set. Okay, open interval, closed interval, semi-open interval, semi-closed interval. There are four important intervals are here. What is the open interval? Open interval means any real number lies between two consecutive integers. Here X being any one of the real number, A and B, small a comma small b, given the subset of the element, that is the roster form set of X belongs to small bracket of AB or OR, square brackets, both sides are open side. No, that is called open of this part. That is the first version. Small bracket of AB is or square brackets are both sides are open. Here set of X belongs to R such that A less than X less than B. That is called, it read as open interval AB, small brackets. And closed brackets, both sides are closed. Here A must be closed, B must be closed. That is when the initial and terminal point must be initial point, terminal point. When the here A and B, any two elements must be at left side and right side must be closed. Here that is A comma B belongs. A comma B must be both sides unclosed. That is the square bracket of closed AB equal to set of X belongs to R such that A less than or equal to X less than or equal to B. Because closed square bracket represents both sides less than or equal to is there. Now that is it read as closed interval of square bracket of AB. So A must be closed because and before that there is no elements. And B is the final element is also closed. Final number is closed. So there is no elements after B of that final element. Here it read as closed interval means square bracket of closed interval AB. Now first number A must be closed, B is the open. Open means a small bracket or OR. So the square bracket must be open side. Okay. Now either this one A is closed and B is open. Now it read as A less than or equal to X and less than B. Because small bracket represents less than, square bracket represents the less than or equal to. Now it is left closed, right open interval. So that is called semi-open. or semi-closed means left bracket is open and right bracket is closed. A is a small bracket, B that is the open part. When B is the final element, that must be closed. Final number is closed. Here that is the roster form. Set of X belongs to R such that A less than X and less than or equal to B. Now that is also one of the important. Now here we are taking, this is the symbol of infinite. Okay. Now here the definition is, what is the neighborhood? Neighborhood means according to the neighborhood of the element. So all the any point, at least any one of the element, we are taking any one of the real number is there, and epsilon be any number, that number must be greater than 0. It is also a real number. Now that is the roster form of the neighborhood is denoted by here x be any one of the real number such that x being a real number such that, and absoluteness is defined at x equal to a. It represents mod x minus a. Now we read as x defined at a means mod x minus a less than epsilon. It is called the epsilon neighborhood of small a. So what is the neighborhood of a? A minus epsilon and a plus epsilon. Neighborhood represents in the small bracket in between the a lies between a minus epsilon and a plus epsilon. Suppose just you have to sketch the one of the real line is there and a be the midpoint. So that midpoint is denoted by element is there. So a be any one of the element, any one of the real number lies between left neighborhood is a minus epsilon and right neighborhood is a plus epsilon. So what is the left neighborhood of this part? A minus epsilon and a. Right neighborhood is a and a plus epsilon. So students, listen carefully. What is the open set? A set capital A is open, and before that it has a neighborhood of points and interior points. Yes, now a set is consisting when the neighborhood and interior points, that is called open set is there. Okay. Now here what is the x? Here x being any, x is consisting an open interval. Every open interval is an open set. Suppose open interval is denoted by a small bracket of AB. And one of the example of open set is open interval AB is an open set. Here A comma B both are two real numbers. Okay. Now that interval, open interval is consisting of the element is x, a less than x less than b. Now x is the neighborhood. That neighborhood is represented in the terms of del must be greater than 0. That is the existence of this part. Now open interval is x minus del and x plus del. Now in terms of del representation of that element, that is the neighborhood of this part. Here x minus del and x plus del is contained are equal to a and b. It is also open interval a and b is contained are equal to Kepler. Now here x minus a and b minus, that is the del value lies between, that is the minimum representation x minus a and b minus x, because here a and b both values are in between the element is x is there. So that is mod x minus a means x defined at x equal to a. B minus x means defined at x equal to b is there. Okay. Now here one of the open sets. Real numbers is also open set. Empty set is also open set. Now here the neighborhood of x minus epsilon, x plus epsilon is contained are equal to Kepler. Because here empty set means there is no points, because it satisfies the definition of open sets. Because there is no elements given in the empty set, then automatically it has neighborhood of points and interior points. So then automatically a set is consisting neighborhood and interior points, that is called an open set. Okay, in the same manner there are so many. 2.2.6 is also a with there is not open set means rational numbers is not open in real numbers. So that is because there is no interior point. So every open interval is an open set, or the union of open intervals. Every open set in script R. Double R means that is the script R. The set means the system of real numbers. The set of real numbers is denoted by Kepler. Now script R means double of the representation. Every open set in script R is a union of open intervals. This is also one of the simple 2.2.7. Now and before, when we must learn entire the concept of real analysis, through the real number system. What is the open set and closed set and limit point? Now then easily to practice and easily to higher levels to practice the higher level mathematics. That is the post graduation level. That is the entire the concept of real numbers must be analyzed in the set theory, sequential part, series part, infinite series part, and even real functions. And now that real function must be the continuity part, differentiable part, okay, and integrability is also there. Okay, enter that is the calculus when the real numbers must be calculated through the sets and functions. So that is called calculus, means that is the when we must practice continuity and derivative and or derivable or differentiability and integrability. That is the calculation. So enter the calculus, real calculus, in the same manner that is called real analyzation of this part. Okay. So 2.2.7, this is also one of the important. What is the closed subset? 2.2.8, this is the simple definitions. That is not necessary here. And students listen carefully. 2.2.11, this theorem is very important. Complement of the open set is called complement of the open set. That is called the closure of this part. A set, if it is not open, that is then automatically that is called closed set. Okay. Now 2.2.11, this is also one of the important theorem in the final examination. The intersection of two open sets is an open set. The intersection of two, when the just A and B be any two open sets, in between the intersection A intersection B is also open set. Okay, the union of any collection of open sets. Collection means there are number of open sets is there. A1 union, A2 union, A3 union. There are number of. It is simply represented union of I values. Here I being the index of the values. That is capital A base I. Union of AI is also open set. That is the second statement. These theorems based on the open sets part. The intersection of any two or the finite intersection of any two open sets is also open set. The family of union or OR, the union of any collection of open sets is also open set. Now this is also one of the important theorem 2.2.11. Please listen carefully. That is the simple proof. This is also one of the important essay question in the first block especially. Here, first one, A and B be any two open sets. The intersection of the subsets is at least one element is taken, X being any one of the element. That is the intersection of the A intersection B. Here X is consisting A and X is consisting B. That is the roster representation. Okay. Now here any neighborhood is there, epsilon I, that must be greater than 0. What is the neighborhood representation? Capital N of epsilon I with respect to X, must be contains capital A. In the same manner, X is also consisting B because B is an open set. Open set means that is the representation is neighborhood representation is capital N of epsilon 2 and X contains capital B because epsilon 1 of the neighborhood contains A, epsilon 2 is the neighborhood contains capital B because the minimum values of epsilon 1 and epsilon 2 is denoted by epsilon. So by the open set definition, N of epsilon and X contains because X is the common element and common neighborhood of the minimum value represented by epsilon. So N of N means that is the neighborhood of this part. Epsilon with respect to the X contains A intersection B. So X is also consisting. That is the meaning of X is consisting A intersection B. That is also an interior point of A intersection B. So then automatically A intersection B is an open set. In the same manner, union of the representation means AI set. In the AI set, there are number of sets are there. A1, A2, A3, so on. Okay, so X is the common element, every set is there. In X belongs to A1, X belongs to A2, X belongs to A3, and every set must be the open. So then we must write in the union with respect to the union of this part here, that is, yeah, A1 set is the neighborhood is epsilon 1, A2 set is the neighborhood epsilon 2. There are number of neighborhoods. So union representation is the maximum of this part. Okay. So finally, n of epsilon and x contains capital X. So that is also capital X is also union representation. So that is union of AI. Is also common element is capital small x is there. N of epsilon and x contains capital X. X is open is there. Okay. So that is the one of the important theorem. Students, listen carefully. Finite number of open sets of their intersection is open. But if given the converse is not true, because so arbitrary number of open sets is also open, the intersection need not be open set. That is the simple example is because an equal to minus 1 by n and 1 by n. Because here n being a natural number, 1 by n lies between, it is greater than or equal to 0, but it is less than 1. Because single element is 0. So union of the arbitrary of the open sets, intersection of an is not open, through an values is open. Okay. Now this is also one of the important theorems, students. This is the second unit. Now last but not least, here especially the union of countable collection of disjoint sets is open. Okay. Now that is any non-empty open subset of real numbers is a union of countable collection of disjoint open sets. Okay. This is also one of the important theorem, 2.2.14. 2.2.14. This is also one of the important. Should listen this one, especially through this is the definition. State and prove Bolzano-Weierstrass theorem. Now enter this theorem must be based upon the limit point of a set. Okay. What is the limit point? Okay. So a point here, any one of the real numbers, the set of real numbers is denoted by capital R. At least one real number is denoted by small a. Here small a be any one of the point being a real number, that is called a limit point on of aggregate. If every neighborhood of a contains a point capital A other than itself. So AB is the neighborhood A minus epsilon and A plus epsilon, or A minus del and A plus del. But because here A does not consisting of the element, because A must be a real number is there. So then it is equivalently a real number is a limit point. Now that limit point is also contained, the subset is capital R. If every neighborhood of A contains an infinite numbers, if infinite number of members, that is called the limit point. Infinite number of members. So here X is this is the meaning of every neighborhood capital N of small a, n intersection A is an infinite set. Sometimes a limit point is also in sometimes it read as accumulation point or cluster point or condensation point. Okay. Now these are all similar names in the replacing of limit point definition. Okay. Now students listen, an infinite bounded set, it has a limit point, at least one limit point. Now that is the statement of definition is there. See the definition 2.3.3. This is also one of the important definition. And through this definition, we must prove the Bolzano-Weierstrass theorem. Okay. The set of all limit points of an aggregate capital A is called, limit points of the set is called a derived set. Okay. 2.3.3. That is the definition is called a derived set. Derived set is denoted by A dash. Okay. Set of X being a real number such that X is a limit point of A. When all the set of all limit points is called a derived set. Okay. What is the closure of A? A union A dash. A union A dash is called a derived set. So empty set is a finite set. And set of all integers do not have the limit point. Okay. Because there is no elements. Next, 2.3.5. What is the limit point of set of 1 by n? That is a simple limit point is 1 is only one limit point, that is 0. set of 1 by n such that n being a natural number, limit point is dash. The limit point of set of 1 by n such that n being a natural number, that value is 0 because it has only one limit point, because 0 less than or equal to 1 by n and it is less than 1 is there. Very important concept, because n being a natural number means that is n is greater than or equal to 1. What is the reciprocal? 1 by n is greater than or equal to 1. And the reverse of this part, 1 by n is greater than or equal, 1 by n is greater than or equal to 1 means 1 is less than 1 by n. Because 1 by n is less than 1 is there. 2.3.6, every point of real number is a limit point. Because infinite number of points is there, the derived set of the real numbers is also a real number is there. Okay, now this is also one of the important definition, and student listen carefully. Okay, a set is closed if and only if derived set is a dash is also a subset of A. Okay, now 2.3.9 theorem, just you have to see and refer by the basement of definitions. 2.3.9, a set capital S is closed if and only if its complement is open. In the same manner, through the definition of closed set and derived set, a set S is not open means given the set is closed. The aggregate set is closed if and only if derived set is a subset of A is there. Now, 2.3.10, this is the concept of union of the concept of capital A and A dash, because closure of A is denoted by A bar equal to A union A dash. Okay, it read as closure of A. Now, students, listen carefully. Now, this theorem is also very, very, very important in the final examination. That is 2.3.11. That is the theorem is Bolzano-Weierstrass. State and prove Bolzano-Weierstrass theorem. Without this theorem, we can't expect the final examination. That is, every infinite bounded set has a least point or has at least one limit point. Okay. So listen carefully. Every bounded infinite aggregate set has a limit point. That is the simple statement of Bolzano-Weierstrass theorem. Bolzano-Weierstrass, both are single mathematician. Now there are different. Bolzano is one of the mathematician and Weierstrass is also another mathematician. Bolzano, he was express finite number of members, and Weierstrass is the infinite number of members. But concepts are same. Limit point is also at least one limit point is the same. Okay, but so given the bounded, a bounded infinite bounded set, if an infinite bounded set has at least one limit point, that is the statement of Bolzano-Weierstrass theorem. Suppose capital A is bounded and infinite aggregate, because AB is the lower bound and B is the upper bound of this part. Given the set representation, that is the set of X being the real number such that minus infinity to X intersection of A is the at most finite is there. He was express, Bolzano, he was the express of the given the set is there. Now, minus infinity to A and intersection A is the empty. So here A being one of the given the element given in the set and S is an aggregate and X is greater than B is there. Okay. And here minus infinity and X intersection A equal to capital A is there. Suppose given the set, that is the infinite set. So then automatically X does not consisting of S. When the X belongs to S is there, and then XL is less than or equal to B, because here that is the condition of upper bound definition. B is an upper bound of S is there. Now a set of real numbers which is bounded above as supremum. Supremum means that is the least upper bound of the given the set exists is there. So that value is say small c. Here epsilon be any number. That number greater than 0, there exists X belongs to S such that. Now what about the what is the neighborhood of X with respect to the supremum of the value? So X lies between C minus epsilon and C is there, because that is the finite number of S. and infinite number and infinite extended real number system minus infinitive and C minus epsilon and intersection A. Okay. And intersection A contains minus infinitive is the C minus epsilon value is say X is there and minus infinitive X and the intersection of A is there. But here Weir stress, there is Weir stress especially explains, it explains infinite number of members. So minus infinitive X intersection A is at most finite numbers, that is X belongs to S is there. So minus infinitive C minus epsilon intersection A is the set at most finite is there. So is the C value is means least upper bound of the set, that value is supremum, and upper value is the upper neighborhood of the value C plus epsilon does not consisting of S. So finally, minus extended real number system and minus infinitive and plus infinitive, and that is the near value is the C plus epsilon minus infinitive and C plus epsilon intersection A is in finite. Now finally, neighborhood of the value of the supremum C minus epsilon and C plus epsilon intersection A contained are equal to minus infinitive and C plus epsilon intersection A. That is the infinite set. So finite and infinite set, number of members it having finite number of finite, that is number of members. It represents the number of members. So then automatically that supremum value is a limit point of given the set is there, subset is there. Okay, should listen carefully. This theorem is also very important. Please note down 2.3.11. That is the Bolzano-Weierstrass theorem. Simply, it has greatest limit points theorem, least and greatest limit points theorem, 2.3.14 in the same manner. That is the one of the corollary of Bolzano-Weierstrass theorem. Okay. Now the set of all interior points is called denoted by interior points of the set is denoted by I of A. Interior point set is denoted by capital I of A. Okay. Now this is the one of the worked example. This is not necessary here because due to lack of the time. 2.4.2. This theorem is also it depends upon the subsets. 2.4.2. S and T both are aggregates, and S dash T dash represents the derived sets. So and aggregate sets and the derived sets of the principles represented as S contained T implies S dash contains T dash. T dash. This theorem is also very important. 2.4.2 is there. Okay, please note down 2.4.2. This is also one of the important relation. Finally, the short notes, the derived set of a set is closed set. 2.4.3. So this is also one of the important theorem. Students, there are 2 units complete in this session, especially now this is the last class. Maybe I have finished the especially third block, and especially in the first block, first and the second unit both are is also completed here. Now only there are 6 classes. This is the last online class. Now the one of the reference, especially these classes are very most useful in the final examination. Now just you have rewatched again and again again in the YouTube of this part. Okay. Now these classes are very important to thoroughly repeated and see and watch again in YouTube is there. BRAOU Live 4. I am Srinivas Rao V. My contact number is 9989476833, and personally contact through WhatsApp for your doubts. Okay. Now so one of the important model paper is also there. Now I must post it BF maybe tomorrow and the day after tomorrow. The final examination model paper is also just I also inserted in WhatsApp group is there. Okay. So don't miss it. So once again, wish you all the best and wish you good luck. Thank you one and all. Hello. Thank you one and all.
Thank you, sir.
Thank you, sir.
Most
Thank you,
welcome.
sir.
Most welcome. Double nine Kepler 9989. Once I repeat this number 9989 476833. Please just see and hear 9989 476833. This is my number. Okay. Once again, wish you all the best and wish you good luck. And wish you good luck in the final examination, especially. Okay. No doubt. I will post it and maybe maybe tomorrow and the day after tomorrow I will give and submit the one of the question paper is there for your purpose, especially in the final examination. This is not theoretical part because this is mathematics. There are no, everyone is important. Okay. UZ third year. UZ third year. UZ third semester group. Third semester. Okay. Thank you one and all once again. Wish you all the best.
Thank you, sir.
Okay. Sure. I will send.